Are you sure? Am I audible?
Yes, sir.
Yes, sir. Okay. Welcome. I welcome to our participants and our today's speaker, Mr. Ayush Patidar, sir. And without wasting time, I request to Mr. Ayush, sir, to take today's lecture.
Okay. Thank you, sir. Thank you for such a warm introduction. Hello, everyone. Good afternoon. And let's start with our today's session. So up till now, I think you have been introduced with the OpenCV and basics of OpenCV. What are images? How do you open an image? How do you process an image? Blurring and drawing on images. All these things you have been taught, or I think it's covered. Right? Okay. So our today's objective would be to detect different, object detection, basically objects in an image from an image. Right? So the main thing that we're gonna look today is how to detect faces in an image, right? So facial recognition is one of the critical problems of sort of any visualization or OpenCV based project, right? So suppose, for example, when we took selfies from our mobiles, right? When we open our front camera or anything, right? So you see naturally there are some boxes drawn around your face. So how is that done, right? Our camera is automatically detecting our faces. So there has to be some algorithm or some kind of process to detect those faces. So that's what we are basically looking today. So how do the bounding boxes appears? How do we detect faces in any stream or in any image, right? Video or anything? Okay. So without wasting any time, let's start with what is the process and how we'll do that. Okay. So let me first, before I start with the coding and sharing my screen, all those things, let me just introduce you to just a little concept that we're going to use that will be helpful for detecting these faces. So in any object detection procedure or an algorithm, when we detect something from an image, right? So for that, there has to be a model that is trained or that is utilized to detect those faces that will search for a face in the entire image, right? So in our case, in OpenCV, that model that is used to detect any object is called a cascade classifier. Okay, so its name is a cascade classifier. So what is this cascade classifier? So it is nothing. It's simply an XML file. Okay. It contains a bunch of data. It's basically a pre-trained model, you can say. Okay, we'll just it's readily available on the internet or even with the OpenCV documentations or OpenCV package. When we install it, it comes inbuilt with those, right? So this XML files we can use to detect any object, right? For all the detection, suppose if you want to detect face, so there is a separate cascade file, XML file for that face detection. If you want to detect eyes, for eyes detection, there's a separate file. If you want to detect number plates or anything else, so for all those tasks, different tasks, there comes different XML files. And how are these files generated? So these files are basically trained on a large data set. Uh, before that's a background process I'm talking about, right? We won't be needing to train these files or create these files. These files are already available. We will just use those files directly. But just to let you know how was this file generated or how this cascade classifier came to exist. So for that purpose, I'll just brief you about the process of how this file is created. Okay. So for that purpose, what people do is they collect many hundreds and thousands of images. Suppose you want to detect faces, right? So they will collect thousands of images containing faces, and they will also collect thousands of images in which there is no face, right? both positive and negative images would be collected, right? And then they will a model would be trained, right? Basically, it's a part of an ensemble learning classifier. So that's the process. You'll if you sometime learn about machine learning in detail, you'll get to know about it. But yeah, so they use some learning techniques to train a model which will just read these images and will understand, okay, this is the image, it contains space. This is the image, it does not contain any space, right? So it will go through all the images and will learn, and all the learnings that is gathered through this process will be stored in an XML file, and that XML file is available to us. We can directly use it, and all using that past learning, our model will tell us whether there is a face for the object that we are concerned with in that image or not. Okay, so this is the basic background of how these cascade classifiers are trained or how they came to existence. So if anyone has any doubt regarding this, you can go ahead and ask. No issues with that. So now let me share my screen so that we can start with the actual implementation. Is my screen visible? Can anyone confirm that?
Yes, sir.
Okay, yeah, okay, thank you. So let's start with the face detection. Okay. So as I mentioned, yeah, we'll be using R cascade files. These are called cascade classes. Okay. So these are used to detect anything. So first of all, we'll be doing two things. First, we'll detect faces in the image, and then after that, we'll move on and we'll also detect eyes in it. So for that, basically, okay, is this screen visible or should I increase the font size? I think this would be quite clear. Okay. Okay. So basically, we have a data folder. In that, there are certain JPG images. Basically, these are images of some people on which we'll be detecting faces. And there are these XML files you can see. There are these 3 XML files that we'll be using today. One is Har cascade frontal face report. This will be used to detect frontal faces of any object in the image, any person in the image, basically. And there is this Har cascade eye.xml. It will be used to detect eyes. Okay. So we'll import this files and proceed. So let's start.
Excuse me, sir.
Yeah.
Sir, can you share these files in WhatsApp group so that I can also practice along with you?
Okay. Sure. I'll share these files right now. No issues. Just a minute. Okay. Okay, so I have shared the files. They should be available to you in a while. Okay, please confirm if you get the files. So basically, I have shared all the files, images that will be working with, and video that we'll be working with, and also the XML files. Okay, for face detection and eyes detection. Okay. You guys can import those files, and you can work alongside. Now, we'll start with oh, face detection. Okay, so one word of caution over here would be that these are not any facial recognition thing, right? It's just the detection. Okay, detection means in image will be detecting a face, if there is a face in that image or not. So that's what we'll be detecting. We won't be recognizing whether whose face is that, right? If there is a face in an image, our model will just show a bounding box, or will just tell us that there is a face in that place.
कौन सा BK है जिसमें
Hello. Hello.
Yes, sir. Please continue, sir. There is
Okay.
some noise.
Okay, sure,
Oh,
sure, sure.
okay, sir.
So our model will only tell us whether there is a face in an image or not, and if there is a face, at what place that face is there. Okay, it won't tell us whose face is that. For recognizing whose face is in an image, there are some advanced concepts or advanced algorithms available in deep learning that will not be covered today. Our today's concern is just detecting any faces in an image. So let's start with importing the required libraries and packages. Okay. So we'll be importing two libraries. First will be CV2, that is basically our OpenCV library, which is used to read the files and process the files. And also CV2 is the library that will be used to load this Hierarcascade files. Okay. Another is the matplotlib library. Okay. So we are importing matplotlib library just to plot the images. So to show these images, display images and our results, whether the faces are detected or not, for that purpose, we are importing matplotlib library. So these are the two libraries that we'll be using. Now, after that, let's start with reading the images. So as I already mentioned, in the data folder, all the images and videos and XML files are kept that we'll be using today. So first of all, let's read the three images that we'll be using to detect faces. Okay. So as you have already learned, right, in order to read an image from using OpenCV, so there is a method called imread, right, in CV2. So we'll be using cv2.imread, and in that method, to read an image, what we will pass? We'll pass the path of the image along with its name, right? So our image is in data folder and its name is suppose this one, Nadia underscore Mura, right? So we'll pass the entire thing, right? Data folder, inside that our image is Nadia underscore Mura.jpg. Yeah. So in this way we can pass the entire path of the file that we want to open. And there is the second parameter or argument that we are passing to this, right? So this 0 basically tells that read this image as a grayscale image or as a black and white image, right? So if we won't pass 0, it will read our image as a colored image, right? RGB image. If we pass 0, then it will read our image as a black and white image. So basically, most of the time when we are detecting images, we generally work on grayscale. We can work on colored images as well, no issues with that. But if we work on grayscale images, it gives us better results comparatively. But mostly in real world, we don't bother converting into grayscale images just to save the efficiency for efficiency purposes, right? Just to save some processing. Okay, so here we are reading three images. Okay, so one is Nadia underscore Mora, one is Dennis Cookwick, and one is Solvay. So now in the next line, let's use matplotlib to show display this images, right? So the command is plt.imshow. As you all know, imshow is the method in matplotlib which is used to display the images, right? And what are the images that we are going to display? First, let's display this Nadia image, right? And we'll pass CMAP equals to gray because this we have read this image as a grayscale image. It's a black and white image. So that's why we are passing CMAP equals to gray. If it would have been a colored image, then we won't be passing this. We will just pass this name like this. Okay. Since it's a black and white image, we'll have to pass CMAP equals to gray. Now let's run it and have a look at the image. Okay. So as you can see, this is the image that we have read. So will be using this image to detect a face, right? And so moving on, let's look at the second and the third images, right? So this is first image, this is second image, and this is our third image, right? Now, looking at the images, what we can see is in the first image, the face is quite clear, right? Because we have light background, and in light background, our faces or our entire structure of the body is quite clearly visible. So this is a quite clear image. In this case, the background is quite dark, right? So the face, boundary of the face is not quite clear, right? It's somewhat not visible. So it would be a this kind of images are sort of called some challenging images, because we are trained an algorithm for a model, so it doesn't always work perfectly. So these are the kind of images that actually challenges or actually test our model, whether it's working correctly or not, whether it's performing good in these challenging situations or not. So we'll test it on this image also. Now, the third image, this is of a conference, a Solvay conference. It's famous conference of physicists. It was held in somewhere around early 1900s. Okay, so this image, you can see there are many faces, right? It's a group image, so there are many faces. Now, our model or our classifier, cascade classifier, it should detect, basically, ideally, it should detect all of those faces from this image, right? So that's our purpose. Now, if you see, if you look closely, there are many faces, and some are in the light background, some are in the dark background, some are clearly visible, some are blurred. Some of the faces are not looking at the front. Suppose if you look at this persons on the top right side, some of them are looking at either left or bottom. So so this image is not quite clean, right? You can see. So this will also be a challenge for all these faces, right? Some of them would quite easily be detected. So let's see. Okay, so we'll be using our cascade classifier to detect faces in these three images. Now moving on to our classifier. Now, how do you read classify this? So reading and displaying images that you have already learned. So this is quite easy part, right? Now this would be new to you. How to read this cascade file or this XML file that we have kept. Right? So in order to read this file, there is a method in CV2 called cascade classifier. So when we write cv2.cascade classifier, this function basically, this method basically reads our XML file. So inside this, we'll just pass the our path to our XML file. So our XML file is in data folder, right? As you already seen, inside the data folder, here is our file, our cascade frontal face XML, right? Default XML. So we'll pass that entire thing over here. Data folder, inside it, there is a file called harcascade underscore frontal face underscore default.xml. Okay. So when we pass the path of the file and call it inside the cascade classifier method, we'll get an object, face cascade. Now this variable or object, whatever we call it, this will be used to detect faces. Okay, so this is how we load a classifier, cascade classifier file. So when we run this cell, the classifier will be loaded in face underscore cascade variable. Now we can use this variable to detect faces in any image. Right? Now, face detection is basically two-part. Right? How is it a two-part thing? Basically, this variable will be used to detect faces, and when we'll use this on an image, what this will return to us will be the coordinates of the boxes, bounding boxes. Basically, uh, suppose let me run it first, and then I'll explain to you that better. Okay. Suppose like this, we have detected a face and we have created a bounding box, right? There is a box around the face. So what this function will return to us when we predict faces on an image. It will return to us coordinates of this box, right? At what point is the top left corner? What point is the bottom right corner? This will be the coordinates, right? These coordinates are returned to us by the classifier if it detects any face. If it doesn't detect anything, it will return nothing. It will return none to us. Okay. So these are the things returned to us. Now it will just return the coordinates of this box, right? Now to draw these boxes, we'll have to draw this box ourselves, right? So as you have already learned how to draw a rectangle or how to draw anything in an image, right? There is a function called cv2.rectangle. We'll be using that function to draw this bounding box. We have already got the coordinates. We just have to draw this. So to do both of these things, right? To detect or get this coordinates for this box and then drawing this box, we have created a function. Okay. We have created a function that will do all these tasks in a single place, right? So that we don't have to type all the code again and again. When we'll be using this thing on the 3 different images, we'll just call this function and it will do all the things for. Okay. So now what we are doing inside this function, okay? Function's name is detect_p, right? It's taking an image as an argument. We'll pass our image to this function. Now what will this function do? This will initially, it will create a copy of the image that we are passing. Why is it creating a copy? Why are we creating a copy? Because if you recall, when we draw anything on an image, when we draw a rectangle or anything on an image, it basically changes the original image itself, right? It draws on the original image only. So in order to keep our original image intact and draw these bounding boxes on a different image, we first create a copy of our original image. Okay. So that's why we are using image.copy function. So it will create a copy of the original image and name it face_image. Now we'll be drawing bounding boxes on this image so that our original image is still intact. Okay. So there won't be any changes in our original image. So to create a copy, this is our first one. Now after creating a copy, now what we'll do is use our classifier to get the coordinates of any faces in the image if there exist any faces, right? So to detect that, to predict faces, what we use is this our object or what you call variable face cascade, right? There is a method inside that. So we'll use a method of that face cascade, and that method's name is detect multi-scale. Okay. So always the method would be with the same name. The name of the method is detect multi-scale. This will detect the faces and will tell it to us. And if our cascade classifier is of detecting eyes, this detect multi-scale will detect eyes. If it's of detecting any number plates, also this detect multi-scale will return coordinate of the number plates, right? So whatever our cascade classifier is intended to do, this method detect multi-scale will remain the same, and it will do the required task. Whatever the classifier is supposed to detect, it will detect and return the coordinates. Okay, simple. Now, this name face cascade, it can change. It can be anything, right? Suppose if you want to give it a name ABC, you can give it ABC, but provided here you will have to call it by that name, the ABC.detect multi-scale, right? So it could be anything. It depends on us. So for readability and for easier understanding, we name variables and objects in we name them according to their function so that it's easier to understand what it's supposed to do, right? So this is basically our cascade classifier for face. So that's why we have named it face_cascade. Right? So now face_cascade dot detect multi-scale. Right? It will return us the coordinates of faces in an image. Now what will pass to it? Will pass face_image basically, right? Or that's our this image, that copy that we created of the original image. We have passed the image to it, and it will detect coordinates in this image and it will return it to us in a variable. Okay, right? So this function will return us the coordinates of the detected faces. Right? So now uh, this is basically a list, right? It won't be a single coordinate, right? will list. Suppose if there are many faces in an image, so like in this conference image, right, there are multiple faces, so it will return coordinates for all these faces, right? The first phase it is at this place, second phase it is at certain position, third phase is at certain position, so it will have to return coordinates of all of the faces that it has detected, right? So what it returns is a list of coordinates, right? So to access all the coordinates in this list, we'll have to loop through this variable, right? So we'll use a simple for loop that will loop over all this face underscore rectangles. This is face rect stands for face rectangles, right? The coordinates, right, of the bounding boxes. So it contains all the four variables, right? X, Y, W, and H. What does this stand for? X stands for the X coordinate, Y stands for the Y coordinate, right? X comma Y basically. So that would be our top left coordinate, X comma Y, right? It returns four things. First is X comma Y, that is our top left corner, and the third and fourth are width and height of the bounding box, basically. So using width and height, we can calculate the bottom right corner or any other corner that we wish to calculate, right? Suppose we want to calculate the top right corner. So it would be nothing but the x coordinate of top left plus the width, right? It would be the right corner. So simple. So that's why in OpenCV generally wherever you use any detection or any sort of technique which returns coordinates, it generally returns coordinates in this format only. It will return you x coordinate, y coordinate of the top left corner, and the third and fourth will be your width and height. Okay. So using this four, you can draw any box or bounding box, or you can calculate any other coordinate or corner if you like. Okay. So now we have looped over these rectangles. So it will give us all the rectangles one by one. And inside this loop, what we'll do is use these coordinates to draw rectangle. Right? Initially, first phase, it will give us x, y, width, and height of first phase. So we'll use cv2.rectangle method to draw a rectangle. That's a bounding box basically, right? Now, cv2.rectangle you have already studied. This function will, what it will do, it will basically take the image on which you have to draw the rectangle, right? The coordinates of the top left corner is at x comma y, right? The coordinates that we get from this, and coordinates of the bottom right corner. So rectangle takes three basic arguments, right? The important arguments. First is the image on which you have to draw. Second would be the coordinates of the top left corner, and third would be the coordinates of the bottom right corner. So how do you get the coordinates of bottom right corner? Now, getting the coordinates of bottom right corner is quite easy, right? The coordinate of top left corner plus its width. So x plus w would be the bottom right corner x coordinate, and y plus its height would be the height y-axis coordinate of the bottom right corner. Right? So in this way, we get coordinates of the top left corner and bottom right corner. Now the next arguments are nothing but some visual changes. This is basically the color of the bounding box, and what color you want to draw it. 255 to 55 to 55 means it would be a white color bounding. If you pass all of the zeros, then it would be a black color. If suppose these two are 0 and this is 255, then it will be a red color bounding, and so on. So we can decide these are basically RGB values. We can use any RGB value, customize the color of the bounding box according to our needs, depending on the background of the image, which color would be quite easily visible. Right? So we can change this. And this last coordinate is the thickness of the bounding box. How much thicker or broad bounding box we want to draw, right? This line, the line of the bounding box, how much thick line that we want to draw. So it's the thickness of the bounding box. So these are the basic parameters that we use to draw the rectangle, right? So what this entire thing, this loop will do is, it will take the coordinates of the first phase it is detected, it will draw a rectangle, right? Then it will again loop, it will take the coordinates of the second rectangle, second phase, it will draw the second phase on the image. Then it will take the coordinates of the third face. It will draw the third face, and so on until these coordinates are, I mean, all the faces are drawn, right? This list is empty, right? It will draw and take coordinates of all the faces that it is detected from this list and draw all of those on this image, right? And what it will do is finally return this image to us. So in this image, all the faces will be drawn. So this is a basic function that we have created so that we don't have to do this again and again on different images, right? For all the images, now what we'll have to do is just use this detect face function and pass image to it, and it will return to us image with all the faces drawn. So we won't have to do anything else, right? So this is a important function for us. Right? So now moving on, right? So what we have done here is we have passed the image of Dennis to this function, and we have stored the result in this variable result, and then we have used our matplotlib imshow to display this result. It's a grayscale image, so we have used it to display. Now you can see it has returned to us image with a bounding box on the face, right? So it has detected the face pretty good, right? It's quite easy to see. It was easy for the model to detect the face in this image. So we can say that our model is performing quite well. Now let's test our model on the next image, that is the image of Nadia, right? So we'll do the same thing. We'll use the detect underscore face function and we'll pass this image to that, right? And we'll display the result, right? So here also you can see it has done quite a good job in detecting the face. The face has been detected and we have got the bounding box over the face, right? Now the next thing, suppose now let's try it on the conference image, right? To solve it. So this would be quite a challenge, right? Because there are so many faces and they are small in size, right? So now look carefully to this image. What are the results that we have got? So most of the phases are detected, right? As you can see, most of the phases it is detected, but there are some errors or misreadings in the phases, right? Namely, okay. So you can see here in the top part, right? There is a fake detection. Basically, it has detected a face over there. There is nothing in that place, right? So that's a wrong detection. If you can see over here, right, this face, it has detected it twice. There are two bounding boxes, but there should be only one bounding box, right? Same goes for this face, right? It has detected, it has drawn two bounding boxes over here. So there should be only one. So these are some mistakes in this detection. Another mistake is over here. It has again drawn two bounding boxes where there should be only one box, right? So there are certain errors in this image detection, right? So now what we can do, right? Is there anything we can do to correct this or to change this face detection and everything to get a better result somewhat? So what we can do is this function that we have created, we can modify this function. So this method, which basically detects faces, it takes some more arguments. We can pass some more arguments to customize this detection, to control this detection, at what rate it detects the faces, right? Should it detect all the faces, or should it be really picky about detecting a face? If it's 100% sure there only it should detect the face, right? So these things we can control. And how can we control this? So basically, if you see, uh, will redefine this function. Everything else remains the same. Okay. So we'll take the image as an input. We'll create a copy so as to keep our original image intact. Then we'll use detect multi-scale function. Now, and here we'll draw the bounding boxes. Everything remains the same. The only change is we are passing two more parameters in this detect multi-scale function. Now, what are these parameters and what this will do? Okay. So basically, these parameters are used to control our image, basically control what we are doing or what we'll get as a result. So this first parameter is the scale factor. Scale factor is by default it's 1.1. So we can change it to any value 1.2, 1.5, 1.8, anything, right? So what does this do? So scale factor, to understand what scale factor does, we'll first understand how this classifier is detecting faces in any image. Okay. So suppose this is the image. Okay. So what our classifier will do is it will create a bounding box. Okay, and it will detect. It will try to detect images in a window of different sizes. For example, right? It will start with a window of the size of the entire image. It will try to detect whether this entire thing resembles a face or not. Right? So there are many other things than face. So it will say no, there is yeah, or it will say there is a face with some less probability, and then it will reduce the window size. So it will try to search for face in this window. Again, it will say, I think there is a face, but not completely sure. Right? Then it will detect in this. So this way, it will reduce the window size in every iteration, and then try to suppose like this, right? It will reduce the window size, and it will search for face in all these windows, right? So somewhere during this process, it will have a window size of this. This will be the window, and it will now it will be more than 90% of really sure that yeah, this window contains only a face, nothing else. Right? So in this way, we get score for all the windows. It basically uh, searches for face using different sizes of windows, and it returns scores for all those searches, right? What is the score, or what is the probability of getting a face in that window? So using that, it finally returns to us a coordinator that this is the place where I'm quite sure there is a face, right? So this is how it works. So the reduction in the window size or change in the window size, right? Initially it was this size, then it reduced to, suppose this was the original size, then it reduced to half, right? So this is the second size. So what is the change in this size, right? So this factor of reduction in the size, this is given by using this thing, right? Scale factor. The scale factor is basically how the window will be rescaled, right? So 1.2 means it will be rescaled by 20%, right? So it will start with a small window. So what it will do is it will start off with a small window, and then it will increase the width, and this window will travel throughout the image and from top to bottom, left to right, and search for face. And then what it will do is it will increase the size of this window by 20%. Right? And then this window will travel throughout the image and search for a face. And then again in the next iteration, this size will be increased by 20%. So it will keep on increasing until it covers the entire image. Okay? So this is how a classifier searches for face in this image. So it takes windows of different sizes and travels or convolves those windows over the entire image and looks for the given object or the corresponding object for which the classifier is trained. In this case, face. So this is the scale factor, right? So we can change what is the scale factor of this, how much should the window size change in every iteration, by what margin, and this is the important parameter, that is minimum neighbors. So minimum neighbors is basically a sort of confidence interval or probability threshold, you can say. The more you pass this number, the lesser faces you will get. Right? Suppose if you pass 7 or 8 in this, so basically in every window, if it's really confident that there is a face, right, then only it will return to us coordinates of the face, right? And if you pass a lower number, then even with the less probability, it will return towards the coordinates, right? So let's try this. We'll try this changes. Okay. So let's run this function and have a look at the results on this image, right? Suppose let's really increase the size of neighbors, right? Suppose we pass 8 neighbors, right? Now let's see the results on the image, right? This is nothing but same. We have called our function with the image and it returned to us the results, right? Now you can see we got really good results, and I mean no extra faces are over there, but we have left out this one face, right? Let's change this scale also. Now you can see we missed quite a few faces, right? There are only certain faces that we are getting, right? Because we have increased the confidence interval and we have also increased the change in window size, right? So it's not detecting all the faces. This face is missed, this entire row is missed, right? All these faces are not covered. Here this one face is missed. Then again, if you see here for both of these faces, there are two bounding boxes, double bounding boxes are made. So these are the errors. So to get a good result, what we'll have to do is we'll have to control these factors, and controlling these factors we can you'll get an idea of what values generally work or what values will be good in a certain situation by experience, right? For initially for starting, you can just use some hit and trial, or basically generally 1.2, around 1.2 scale factor is quite good for that. And you can basically try. So, suppose we take minimum neighbors only 2 or 1, right? Really low, and we increase the scale size, right? Scale. Now you can see we got so many double bounding boxes, right? So all these things, like here, this four faces, all these four faces have double bounding box. This one has double bounding box. This one has double bounding box. So these are not quite good results, right? So these things happen in real life when you have to detect something on any image. Then you won't be sure whether your function would work 100% correctly or not. At that time, you'll have to uh, use these factors, right? You'll have to adjust these factors quite well, or you'll have to use some hidden trial and get to know what are the values of these factors that will work for that particular situation. For every situation, that could be quite different, but mostly for most cases, this setting will work, right? Uh, just have to enhance it a little bit, right? By default, the minimum neighbors is set to 3. So if you just increase it to 5, so it won't give any, I mean, repetitive or redundant results. It will only give results which it's quite sure for. But for with that, it can miss quite a few things, right? Suppose in this image, right? So in this image, we have covered, or we have got all the faces. There's nothing extra. All the faces are covered with only one bounding box, no extra bounding box. Only one thing, only one flaw of this is this particular face is not detected. We have missed one face, but everything else is detected quite perfectly. And there is a good reason why we have missed that face, right? Because the classifier that we have used was trained to detect frontal faces. Frontal faces mean the people who are looking directly at the camera. It can only detect front faces, but this particular person is looking to the right. So our classifier was not trained for that thing. So that's why it has missed that face, right? But if we bring leniency using this parameters, it can even detect that face, right? So initially it was detecting that face, but since we were lenient, so it was also detecting many other things as faces. So that was some wrong predictions also done like this, right? So these are the sort of you can say gain and lose, you can say, right? So if you want to gain something, you'll have to lose something. So you can't get everything, right? So this two parameters can be used to control the leniency. If you are lenient, it will detect more faces, many faces, and it with that it can also detect something which is actually not we don't want to detect, right? There will be misdetections or wrong detections, you can say, right? But if you are strict with this values, if you increase the number of neighbors and if you want to detect only good things, then it will detect perfectly. It can miss some faces, right? So you have both ups and downs of this. So you'll have to strike a balance between the two, right? What works best for you in that particular case, right? So these are the basically two factors which you can use to control this. Now, as you can see in this image, we have done all the things. We got all the faces really good. This one face is fish, but we can't do anything about it. If you want, you can try to adjust these values and try for yourself what will be the different faces or different things, right? Different detections that will come up with different values of these two parameters, right? You'll get to know that mostly either if this face is detected, then there will be many double predictions or mispredictions also. But if you get quite accurate with the predictions, then you'll start missing this face, right? Because our classifier was trained for frontal faces. Now, I leave this as an exercise for you. Just try different values of these two factors and uh, get comfortable with this basically detections, right? So you'll get comfortable with the factors, how this works, how changing the values can affect the this uh, results, right? So this was our frontal face detection classifier, right? So if anyone has any doubt in this, you can just ask me right now. So, okay, if there are no doubts regarding this, let's move to our next classifier, where we'll be detecting eyes, right? So, eye detection can also be done. So, these are the basic classifiers for which these XML files are readily available. Easily, you can just Google them and you can download those, right? So, it's as easy as that. So, uh, this eye cascade classifier and this frontal face detection, these are the classifiers, these are the XML files that come built in with the OpenCV package. So you won't even need to download them if you wish, but if they are available with you, you can use them. Now let's use the eye cascade classifier, right? So to load the file, again we'll do the same thing, cv2.cascade classifier, right? The same method, cascade classifier. This will be used to load the XML file, right? Now, in this case, we'll name our object as eye cascade rather than face cascade, right? Because this cascade classifier will be used to detect eyes, right? Now, so we have named it iCascade and we have mentioned the path. The path is nothing simply in data folder there is a hard cascade underscore i.xml as you can see over here, right? In the data folder we have hard cascade underscore i.xml. So this file is loaded. Again, we'll create a function, simple same function. Instead of detect face, let's name it detect eyes. It will get an image. It will create a copy of the image so as to preserve the original image, and we'll be drawing faces on this copy image, right? So instead of face image, we can name it eye image or something. Okay, so let's save it. No issues with that. Okay. So this is our copied image, right? Now we'll use this eye cascade to detect, right? So eye cascade dot the method will remain the same, right? As I mentioned, whatever the classifier, whatever it's supposed to detect, this method will always remain the same. This method's name is detect multiscale, right? It will be used to detect whatever the classifier is supposed to detect. In this case, it's supposed to detect eyes. So this method detect multiscale will detect eyes, right? We just have to use the object for that classifier that we have loaded over here. Okay, So we have loaded this classifier in iCascade. So we'll use iCascade.detect. There we loaded it in face cascade. So we used face cascade.detect. Okay. Now, to this classifier, we'll just pass the image, right? We will pass this image and it will return to us coordinates. And again, same thing, we'll look for all the coordinates, all the bounding boxes that we'll get, and we'll draw rectangles on all those bounding boxes, right? This part remains same, nothing changes, right? We'll get the xy coordinate for the top left corner, we'll get width and height, and using those, we'll draw a rectangle from top left coordinate to the bottom right coordinate. Color is white and thickness of the bounding box is 10. And we'll have to draw on this face image, right? After drawing on the face image, we'll finally return the face image. So this is a function, simple function that we have created. What this will do is, this will basically take an image, create its copy, detect eyes in that image, draw bounding boxes on the eyes, and return to us the image with the bounding box. Right? Now, let's run and load this. So let's load the iCascade classifier first. Now let's run this function. Okay. So now we have defined this function. Now let's use it. First we'll be using it on the image of Nadia, right? So again, same thing, just pass this image to the function that we have created. So it will do everything and return to us our result. And we'll just, using the matplotlib I am shown, we'll just display our result image, right? Simple. It's just same as above, right? So now you can see it has detected the eye and we've got two bounding boxes, right? Around the eye. So this is our iCascade fixify, right? Now again, let's use the same function, same method on the image of Dennis. So now, when we do this on the image of Dennis, you can see we didn't get any bounding boxes, right? So we got empty list as a result, right? We don't have any bounding boxes, or our classifier didn't detect eyes in this image. And why is that, right? Why? What could be the reason? So if you think about it, when you compare both the images, uh, just look at this image. Here, the eyes of the person are quite clearly visible, right? The white portion around the pupil, right? It's quite clear. You can see the white portion of the eye and the pupil in between that white portion. It's quite clear. The eyes are clearly visible. Eyes are clearly visible. But if you look at this image, right? In this image, the eyes are not clearly visible. First of all, their size is quite small. There's a small eyes, and moreover, the pupil and the white portion around the pupil, it's not quite clearly visible. So it's a tough image for our model, right? So the model is not able to detect those eyes, right? Because of that. Because how the model detects an eye, right? If you look at it in the back end, how the model will, what the model will look for to detect an eye, right? In general, what we do, right? How do we detect an eye? There is a white portion, and then in between that there is a black portion, right? So if there is a white portion and around it there is a curved or a circular black portion, you find it, right? You call it an eye, right? That's the, in layman language or in simplistic terms, that's how you detect an eye, right? So that's what the model will try to do, and that's what the model is trained to do. But in this image, when you'll see, there is the white portion itself, right? The white portion around the pupil, that's not quite clearly visible. And if it's not visible, then there is no to say that this is the white portion and this is the circular pupil, black pupil around that white portion. So this could be an eye, right? So that thing is not visible. That thing is not quite clearly visible. Yeah. So that's why there is a difficulty in detecting eyes in this image. And this just goes on to show us that nothing is perfect, right? So in the world of object detection or machine learning or AI, anything, right? Here, all the models that we train, our aim is to get our accuracy really good, right? About 90%, 95%. But none of our models are 100% accurate, right? because in this image, in this real world, there will always be exceptions. There will always be something which is not quite clear, or which has some misplaced data or something irregular, which won't be trained by, or which won't be detected by our model. Right? Because even this goes on for humans, right? Suppose if, like, training a model and training a person, right? I mean, training a person by training a person, I mean, if let's take an example, right? Correlation. So basically, if there is a student, suppose, right? So if we want that student to give an exam, appear for an exam, right? So we'll give him a syllabus, we'll teach him some concepts, some questions, right? Okay, these are the concepts that you need to learn. He will learn those concepts and he will appear for the exam. Right? So in exam, if the questions are related to those concepts, he will be easily able to answer those questions. But if there is a question which was out of syllabus, or suppose there is a question which he didn't, for which the concept he didn't quite grasp, or he didn't learn that concept, if there is a question related to that, he will have difficulty answering. Right? So he will not be able to answer. So same thing, the same thing that a student faces, or how he learns and appears for the exam, same thing is applicable for any machine learning or object detection model, right? They are trained on a certain images or data set or examples, right? So, as I mentioned at the beginning of the lecture, right, hard cascade files are trained on lots of images, right? Suppose we are detecting eyes in this case, right? So it will be given hundreds of thousands of images containing eyes, and it will also be given hundreds and thousands of images which won't contain any eyes, right? So it will be learning all those images. Okay, these are the type. Or if this thing appears in an image, this is an eye. This thing appears in an image, this is an eye. If this thing is not there, it is not an eye, right? So it will learn from the data set or those images, right? So it will only be able to predict or detect what it has learned, right? So if in the data set that it has learned, if there would have been many examples of difficult situations like this, if there have been many examples of a difficult situation like this, then our model would have been able to predict this also. But since our model didn't learn, or it's not quite comfortable with this thing, so it missed this thing, right? So it's basically same case as whatever the concepts or whatever the knowledge it acquired from learning from those images. This is sort of out of that purview of parameter, right? So it was quite not able to detect. Yeah. Now, here we didn't use those two extra parameters, right? Scale factor and minimum lineage. Now it's up to you. I leave it as an exercise for you, right? You can use these two parameters in this function, right? And then try to detect eyes of 10s. Whether you are able to detect those eyes using those parameters. Make those parameters more lenient, right? If those parameters are lenient, reduce the number of try to reduce the minimum number, right? Try to change the scale factor in either direction, and then see whether still our model is not able to detect the eyes, or whether it's able to detect the eyes by making the parameters more lenient, right? So that I'll leave it up to you as an exercise. Okay, so this is all about detecting any object in an image, right? So any doubts as of now up till here? If anyone has any doubt or wasn't able to follow up with me, or uh, anything regarding any function or any method or any parameter, anything, if you have any doubt, you can ask. Okay, so I guess all of you understood. That's quite good. So if you don't have any doubts, then we'll move ahead. Okay. So now moving forward, this detection part. Now here we have done it on image, right? But in real world, whenever we apply this kind of detections, right, rarely is the case that we'll have to apply it on anything. Mostly we use it on videos, right? suppose you have to count. Suppose you run a store, suppose, right? For example, now you want to count the number of people entering the store in throughout the day, and you don't want to hire a person or someone who will sit at the door and will count the number of people who are coming into your store, right? So what you can do is just place a camera on the door, right, at the entry, and just run a model somewhere like this, which will detect faces, right, or which will detect persons. So it will detect them and it will count, increase the count whenever it detects a face, right? So using such a simple detection model or classifier, you can count the number of people entering your store. It's quite as simple as that. So most of the applications of detection are on videos, right? In real life, mostly will work with videos or live cameras or live feeds, right? So how do you implement this on a video? We have seen it on an image, right? But to implement it on a video, how will you do it, right? So let's start with that. Let's understand how we can change this. What are the changes that we can make to this process, right? In this function, or let's say in this entire thing, to make it that this classifier works on a video as well, right? So for that, first of all, let's understand what is a video, right? How is a video created or how it is made, right? So basically, if you see video, any video, right? Any video, it's nothing but a collection of images. Basically, when you have lots of images and when you play all the images one after the other, when you see all those images one after the other at a high speed, it appears as if the things in the image are moving, right? And it appears as a video. So basically, in layman's language or in simple terms, video is nothing but a collection of images. Right? So you might have heard many terminologies in general, right? One is FPS, frames per second. We call our video, right? What is frames per second of a video? Is it 30 FPS video, 60 FPS video? These terms you can see while using your mobile camera only, right? When we use our mobile camera, when we record a video, there are options to set the resolution and everything, right? There are certain options where you can see it's written 60 fps, 30 fps. So that is nothing but how many frames will it capture in a second, right? As the name suggests, frame per second. So as I said, image is nothing. Oh, video is nothing but a collection of images, right? So if there are, if a video contains 30 frames in a second, right? So all the 30 images, frames means images, right? So it will have 30 images. It will capture 30 images within 1 second. So all these 30 images will move, will be move as a slideshow sort of in a second. So it appears as a video. Now, as we increase the number of frames in a second, right? Now instead of 30, suppose you have 60 frames in a second. Now, naturally, as you can imagine, right, if you'll have more frames, your video will appear to be much smoother because now you have more images within a second, right? So you'll get to see many more images, actually quite double the number of images in a second. So your video will appear to be quite smooth. If you have less number of frames in a second, suppose you have 1 frame per second, right? So in each second, you'll get 1 frame only. So that would appear as if you are viewing a slideshow, right? Normal slideshow. One image will appear, and second, another second you will have another image. Next second you will have another image. Next second you will have another image. So that won't quite feel like a video, right? So it appears to be a video when you have a larger number of frames in a second, right? So as to say minimum 15 to 20 frames per second, right? Then the video appears to be quite stable, right? So the basic FPS that is quite acceptable or mostly popular or mostly used in videos is 30 FPS, right? 20 to 30 FPS is the mostly used frames per second, right? So that's how a video is constructed, right? So it's nothing but a collection of images of same size. Now that's an important thing, right? All the images should be of the same size, right? Suppose one image is of this size, right? Suppose one image is of this size, 600 by 400. Now another image, if you see, if the another image is of this size, 1000 by 700. So both images won't fit on top of one, right? Because they have different sizes. But in video, all the images should be of same size because we are running all the images one by one in a slideshow manner, right? So in a video, we have frames or images of same size, multiple frames in a second. Right? So that's how a video is created or captured. Okay? Simple concept. Now, when you will understand this concept of how a video is made or how it is created, you'll see it's quite easy to implement this detection algorithms on this video. What you'll have to do is simply read each and every frame of the video, right? If you have a video, just read it frame by frame, right? If you're 30 frames within a second, read all the 30 frames one by one and apply the same thing, same function on each and every frame, right? Frame is nothing but an image, right? Suppose this is a frame of a video, right? So what you'll do is just read this frame and apply your detect eyes function. It will return to you the resulting frame and you can show it, right? So you'll just have to apply this function frame by frame on all the frames of the video. That's the basic concept. So what we do is for that purpose there is a method in CV2 called video capture. Okay, so we'll look at this, but before that, uh, I'll show to you the working model and we'll code it, right? On a video, I have already sent you the video through WhatsApp, right? So we'll apply our face detection algorithm on that video also, right? And we'll look at it in working. But before that, before going into that good part, let's just do one more exercise, right? So I have one more notebook. So basically, this notebook is regarding object detection assessment. Okay. So I would really urge you all to uh, work alongside me on this notebook if you can. So I'll forward it to you. Just a second. Okay. I'll send it to you through WhatsApp. So you can work on this notebook alongside. Okay? Okay, so I think
So we get the file.
yeah, okay, you got the file. Okay, so just open it and try to work alongside me. And I want this to be an interactive session. So this will basically what it will do is it will revise you'll be able to revise all the concepts of OpenCV computer vision that you have learned so far, right? So this is basically sort of a project exercise or a task that will involve everything. Okay. So I want all of you guys to participate in it. Okay. So you'll get more confidence and you'll be able to see how we can implement all the things that we have done, or how we can, combine the knowledge that we have learned individually to get a good result or get something that we want, right? So these things are used in uh, synchronization, right? So all the concepts that you have read, right? Like drawing bounding boxes or blurring an image, right? Or how to read an image, how to flip an image, all these things, right? So these things are not individual, basically they are not independent things, right? In a real world situation or in a project or in anything, if any task that you want to accomplish, you will have to combine all these things together, right? As per your requirement. So this is sort of a task for that thing, right? You get to understand this. Now, what we have here is there is an image, right? In this data folder, okay? License plate image. There is an image for a license plate, a car image of a car, okay? And we also have a hard cascade file that's named as hard cascade Russian plate number. So this cascade classifier will basically detect number plates, right? Number plates. So it comes inbuilt with OpenCV. Okay. So this will detect number plates, and what we'll be doing is we'll import this image, load this image of car, and we'll try to blur the number plate, right? That's our final task. Our task is to blur the number plate of that car. Okay. So how we'll proceed? How we'll do this? Right? So let's go step by step, right? First, for blurring the number plate, first we'll have to detect the number plate, right? If you don't know where the number plate is, we can't blur it, right? We know how to blur an image, right? I hope you remember we learned about blurring techniques like median blur and all, right? So we can
Yes,
use
sir.
those things. Yeah. So we can use those things. So let's start with the task. So I'll be coding alongside you. Okay. So let's start with this. So first of all, we'll need to import the libraries that we'll be needing, right? So our first task is to import the libraries that are required. So on the top of the mind, what are the libraries that we'll be needing? First will be the CV2,
CV2.
right?
Yeah.
So import CV2. CV2 will be used for reading the images and classifier and detecting the number plates, right? Other than that,
Matplotlib.
yeah, to display the images, we'll be using matplotlib, right? So as of now, these are the two libraries that we can think of that would be needed, right? So let's import this library. Now, the next task will be to read the file that is situated in the data folder. For me, it is inside the data folder. For you, it could be at some different place. So just pass the path of the file where it is located. Okay. So for that purpose, what we'll do is we'll just read the image using cv2.im read function, right? And what will pass inside this im read function will simply pass the path to our file, right? So our file is inside the data folder and its name is car underscore plate.jpg. Okay. This. So what will it do? It will read our image. So we have loaded our image and it's inside this image variable, right? Now let's okay, are you guys following with me?
Yes, sir.
Okay, yeah, okay, sure. Good job. So now the next thing, right? Let's move on to the next. Next task is create a function that displays the image in a larger scale and correct coloring for the matplotlib, right? So as you know, right, when we read an image in OpenCV, it basically reads the image in BGR format, right? It replaces the red and blue channels, so the colors appear quite weird, right? So it reads in BGR format. So for that, we'll have to convert this image into RGB format.
RGB.
Yeah. So what we'll do here is we'll just create a function, right? And inside this function, we'll write code to display this image, right? We can display the image directly using plt dot I'm show, right? But we want to display this image on a bigger frame, right? So we'll increase the fix size, will convert the image from BGR to RGB format, and then we'll display the image on this big picture, right? So this is the sort of output that we are looking for, right? So we want to get this kind of output. We want to display image on a bigger picture, right? And in color, correct color coding format. So for that, we'll be creating this function. Now, what we will write inside this function, first of all, let's create a fixed size, right? Let's create a figure using plt.fixed size, right? Plt.figure is the function, right? And it takes an argument fixed size, right? Now inside the fixed size, you can basically do the size of the image that you want to display, right? How much bigger image you want to display, and x comma y coordinates, right? Suppose 10 comma 8, right? 10 will be our width and 8 will be our height, right? So we want to display this image on this big portrait, right? Big picture. Now to display this image on this big picture, first of all, we'll have to add an axis. Now there are two things, right? There are two practices we can do, right? First is just use this plt.figure fixed sizes, right? You can change the fixed size and then use plt.imshow, right, to display the image, whatever image you have, right? So this will also do the task, but it's a good practice in general to first of all store this thing in a variable and then assign access to this variable, basically create subplot. What do I mean by subplot? Basically, what we can do in matplotlib is we can display multiple images on a single plot, right? So how do we do that? Let me just suppose you want to display two images together, right? So you can create subplots and display first image on the first half of the plot and display second image on the second half of the plot, right? So in general, it's a good practice, even if you want to display only one image, right? As in our case. So it's generally a good practice to create subplots, right? So we'll do that, right? So we'll create an axis first, right? This axis will contain subplots. So for that, fig dot this figure that we have created will add subplot, add underscore subplot. So what this will do is this will add a plot on which or an axis on which we'll plot this particular image. Now inside this there is a parameter. There are three numbers that we pass, right? There will be three numbers A, B, and C. What are these numbers, right? First number instead of A will pass how many images or how many plots you want to plot in first row, right? Basically how many rows will be there, right? So we have only one row, right? Second is how many columns will be there. So we want only one column, right? And third, on what particular plot you want to plot, right? So we want to plot on first plot. Now, to give you another example for this, suppose if you would have passed like this 2 comma 2 comma 1, right? So what this would have done is it would have created a plot in basically it will have two rows and two columns, right? So it would have created a plot something like this, right? There would have been two rows, 1, 2, and there would have been two columns. And this third number, this one, would depict that we want to plot or show our image on this first plot. If we would write instead of this one, if we would write 2, then it will show a plot or image on the second. If you would write 3, then it will show it on the third plot, and similarly on the fourth if you write 4, right? So these three numbers basically control how many plots we want to create on and on which plot we want to display our image on, right? So this is basically that. So we have single image, so we'll have nothing to worry about. We'll have just one row, one column, single, and we'll plot on the only available plot. So this is generally a good practice to follow. It's not necessary when you are just displaying a single image, but it's good to follow, right? Now, before displaying the image, what we'll have to do is convert this image into BGR, right? So let's take new image. So this new image will be equals to we'll be using the convert color function of CV2, right? This is how we convert an image from BGR to RGB, right? So what it will take? First parameter will be the image that we want to convert, right? And what will be the second parameter? Second parameter will be the color in which we want to convert it from BGR to RGB. Okay? So we want to convert this image from BGR to RGB. Right? So up till now, what we have done is we have created a plot with bigger size, right? And we have defined an subplot, an axis, right? And we have converted our image to RGB. Now we want to show this converted image on this particular plot, right? So instead of plt.dimension, now we'll use this particular plot, right? Suppose if in case we have multiple plots, suppose we have this only one row and two columns. So on first plot, if you want to show something, you can use like this, right? Axis 1, and on axis 1, you can also use something like this, right? This is what we use for multiple plots. On there is one row, two columns, and on the first subplot, we want to we have named it like axis 1, and on the second subplot we have named it axis 2. Now when I will use over here axis 1 dot I am show, this particular thing will be plotted on the first. If I use axis 2 dot I am show, it will be plotted on the second. This is the way how we manage multiple plots in a single figure, right, on a single canvas. Now in our case, it's simple 1 1 1, right? So there is no need for this. So we'll just use axis dot I am show image, right? Now we don't want to show this original image, right? We want to show this converted image, new image. So what will type over here? New image. Okay. So this is our simple function. What we are here is we have just increased the size of the figure, right? This is just for good practice. That's why we have done it. It's not necessary. We have just added a subplot where we'll be plotting our image. We have converted our image from BGR to RGB, and we have finally displayed the image. Right? So now when we'll call this display function, so it will do nothing but it will convert our image from BGR to RGB, and it will display it on a big picture, right? Big canvas. So we won't have to type all this thing again and again. We can just use this function directly. So let's run it and check our output. Okay. So actually, so it's basically it has not displayed the image. Instead, we are getting the coordinates, right? So we must have messed up something. So let's see. So we have created the figure size correctly, right? Figure size is correct, right? There's no issue with this. We have added a subplot in the axis. We have converted our original image from BGR to RGB, and we have used that and show display. So it should display the image. Okay, so we didn't run the function. Okay, sure. Okay, so we didn't run this function initially. That's why it was just not working. So now our function is correct. So we should do that. Now you can see it has displayed this image of this car on a bigger canvas. We can clearly see this. Now our task is, what is our task? Our task is to detect this number plate over here. We'll have to detect this number plate and blur it. Right? So how we'll do this? Right? So let's move on to the next task. Next step. We'll proceed step by step. Now next task is to load a R cascade file or XML file. So what is the purpose of loading the XML file? XML file will be used to detect this number plate, right? So it's used for detection. Now how will detect this? So basically let's load it. It's nothing but underscore cascade, right? So this will be the name given to our classifier, right? And to load it, we have function, okay? save it to the cascade classifier, right? So this is our
Yes.
function. Yeah. So what are the arguments that will pass? Simple, directly will pass the path to our file, right? So what is it's inside the data folder, and what is the name of the file? For me, file there is disturbance for someone's mic. Can you please mute? Okay, yeah. So okay, so this using this command, what we'll do is we'll load our classifier. Okay, so our classifier will be loaded in plate underscore cascade bin function. Now again here, our next task is to create a function that will take in an image and draw the rectangles around what we detect as a license plate. So simple thing that we have done here in the face cascade, right? This type of function we want to create, right? So we want to use this image and draw a bounding box around that image, so that we can be sure that our function is basically our classifier is working and it's detecting numbers, right? So we'll start with this, right? So what we'll do is, first of all, let's create a copy of this image. Enter copy, right? So this function will simply create the image, copy of the original image, so that we don't overwrite it, right? Now, next step would be we'll get the rectangle through our detection. So we'll store them here, and how we'll detect? We'll use this object that we created over here, right? Plate underscore cascade. We'll use this, and what is the name of the method that's used to detect? Right? It would be the same, detect multi scale, right? So this function will be used to basically detect our number plates, right? On what are the parameters? First of all, it will be the input image on which it will have to detect the whatever number plates are there, and then second and third are basically scale factors. Let me just simply copy them from over here, so that we don't have to type them again. Okay? Second and third parameters are nothing but scale factor and minimum labels, right? So these are our second and third parameters. So we'll leave this to as it is as of now. If we don't get good results, then we'll modify them and we'll check on what else we can do, right? So this in this method, what we've done is we have basically created a classifier, right? Now next is nothing but this will also remain the same, right? What we'll do is we'll loop through all these rectangles. We'll name this plate underscore rectangles, right? This is our all the bounding boxes. We'll loop over this. We'll get coordinates x, y, w, x, and we'll plot all these coordinates. Where we'll have to plot? We will have to plot on plate underscore image. What are the coordinates? X, y, x plus y, this, and let's change this color to something else. Okay, so let's try this, right? So I think this is a red color, right? And let's reduce the thickness to 4. Okay, so now we have drawn the bounding boxes. Now we'll return the image. So this is our function as we have done previously. It's the same function. What we are doing is using the detect multi-scale function, right, method on our image, and we are passing these parameters to control the detection, and it will return to us the bounding boxes. We'll loop over it and draw all those bounding boxes on the image and return the final image. So this is our function. Now let's get the results, and let's have a look at the results that we got from this particular function. When we display yeah, okay, so you can see this function is working quite well. So we have detected the number plate and we have got a red bounding box over here, but as you know, our main task was not to draw a bounding box on this plate, right? Our main task was to blur this number plate, right? So what our task is to detect and blur this number plate. We don't want to draw any bounding boxes over here, right? So this function was just to test whether our classifier is working correctly or not. Now we can see that our classifier is working correctly. Now all we have to do is blur this particular region. Now how we will do that, right? So for that, I have given steps over here on what we can do. So what we can do is simply we'll detect this number plate using the classifier. Simple. It would be quite similar up till here, right? We'll get the coordinates of the number plate through this bounding boxes, right? Once we have the coordinates, right, we can select this particular region as an ROI, right? Region of interest. What's the concept that you learned in blending and twisting, right? You have selected an ROI of an image and worked on that ROI, right? So what we can do is we can select this particular part, right? The part that is inside this bounding box, right? We can select that part. We can apply our blurring technique, median blur, for example, right? Let's use median blur. So we can use median blur on that particular part and then again insert that part in this original image, right? So this is the task basically. Just grab this particular bounding box part inside the bounding box, blur it, and then again paste it on the original image. So we'll have to, for that, we'll have to update our function, right? So how are we going to update it and what will do, right? How will apply this thing, right? So for that, the initial thing would remain same, right? So this thing, I think up till here, these two lines would be the same. We'll have to, right? We'll have to create a copy of this image, right? And we'll have to detect number plate, right? Coordinates of this plate. Now what will change is things after this, right? Now what we'll have to do is, first of all, we'll have to loop through the bounding boxes, right? Why loop? Because we'll have to blur all the available number plates that are there, right? So we'll loop through each and every number plate one by one and we'll blur them. Now how are we going to blur it, right? So for that purpose we'll create or we'll select that particular region, right? This particular bounding box region we'll select it, we'll grab it. So for that purpose let's create another copy of this image, right? We'll create one more copy and name it ROI, right? And now from this ROI let's fetch this particular point. So how we'll fetch this thing, right? Simply by using numpy, or sorry, you can call it numpy or normal slicing, right? List slicing in Python, simple concept, right? What we'll do is we'll basically pass in inside this brackets, right? Inside this square brackets we'll pass the coordinates, right? Y and x column x plus z. What have I done over here, right? What we did is from this particular coordinate, right? From this particular till y plus h, right? From top to bottom, and in this direction from left to right, right? X from starting from x ending at x plus width, right? So basically what I have done is basically from top to bottom, from left to right, this particular area, right? This particular area we have selected, right? From top to bottom, from left to right. We have passed this as a number slicing or Python list slicing, simple, and we have grabbed that part from this image and stored it in ROI. Right? Now our ROI contains only the part that is inside this bounding box, right? It does not have anything else inside it. Now what we want to do is we want to apply blurring on this part, right? Simple. So let's name it blurred ROI, right? This function, and how we'll blur it? We'll use simple CV2 function called. You'll have studied this earlier, right? So you should be familiar with that. So what it will take is it will take two parameters. One is the image that needs to blur, and one is intensity on how much blurriness you want, right? So let's pass in 7. Okay, so we want to blur it completely. So that's why we have passed a high number, right, for the kernel size. Right? Now, this is the image that we got. This is our blurred image, right? We have extracted the bounding box part. We have applied blurring on the bounding box part. Now the next step is to uh, paste this blurred portion again on the original image, right, in our plate image, right? So for that, how we'll paste it? We'll simply use this thing only, right? What we'll do is on plate image, right? We'll image in plate image will again use the same part, right? So on the plate image, we'll select this particular part, right, the bounding box part, and we'll at that particular part we'll replace it with blurred ROP, right? So what this line will do is it will replace this particular bounding box part with this blurred image, right? So this 3 line of code will do the trick. Okay. So after that we'll have to do nothing but just simply return our image, right? Now again, what is the 3 lines that are what are they doing? So if we start simply the first line, this will just using slicing, it will just pick up the bounding box part, right? So it will just grab this bounding box, this particular part from the original image. It will grab it. It will blur that particular part, and here it will paste that particular part on the original image again, right? So pick this part, blur it, and then paste it again on the original image. So the original image will remain intact except for this particular part inside the bounding box, right? So it will be updated. Now, note one thing over here. Here we are not basically we are not plotting the bounding box. We are not drawing any bounding box over here, right? We are just grabbing it, blurring it, and pasting it again. There is no bounding box involved over here. So that's our task, right? We want to blur the number plate, right? We don't want to draw any bounding box. So instead of drawing bounding boxes, what we have done is we have grabbed it, blurred it, and pasted it again. So now let's check this function, detect and blur function, right? Let's apply it on our image and let's display the results. Now you can see the results, right? So originally the number plate was quite visible. The number is 0, 333, PA something, right? And here you can see the entire number plate is blurred. So you can't see anything. Other than that, the entire image is still the same, right? So this is how we do things step by step, right? So we had done the entire task one by one. So if you have any doubts in this, you can ask. If not, then we'll move to our final part of the day. That would be how to apply this on a video, right? So that's interesting part. Generally, it's an exciting part, and so there's nothing more about it. Okay, so up to here, I think every one of you is quite clear about it. So what we did was we used the concept that we learned earlier. We have implemented the concept of selecting any part of an image, namely any region of interest, testing it again on an image, applying median blurring, detecting any object through Haar cascade files. So we have basically applied all of the concepts that we've learned up till here, right? So this is how we need to get our tasks done. We need to follow a particular algorithm, or we need to think step by step. What are the steps that we are going to take to reach our final destination? Right? So this is how we do it. Now, so I hope this is done. So next, let's look at the last file, which is our face detection video.py. This is the code for detecting any, what we have done, right? Face detection. So implement our face detection code on our original, I mean, on a video, right? On any video instead of an image, right? So, one word of caution over here. When we do it on a video, right? We want to display a video. So, to display a video, generally what we do is we open another window, right? And that window generally displays a video. So, in Jupyter Notebook, if you are working in a Jupyter Notebook, then videos or opening separate window generally leads to crashing of the Jupyter Notebook. So it's not recommended to use to work any video related work in Jupyter Notebook. For that, you can use any other editor, namely any VS Code, PyCharm, or anything else. Right? Simple ideally would also work. Basic Python. So generally, what we do is we code our video related work in a .py file, right? A Python file, Python script, and either you run it through command line or you run it using any IDE or any other editor. That's up to you. But just don't run this video code on a Jupyter Notebook, because it will lead to crashes in most cases. Sometimes it may work, but it generally crashes your entire notebook. Okay, so that's just a word of caution. So that's why I have this is a .py file. So it's a Python script, right? So we won't be able to execute it step by step. So I'll just go through this entire script once, and then we'll see it in action, right? So first of all, we'll import the required packages, nothing else but OpenCV. We are not importing matplotlib because we don't want to display images, right? We'll be working with video, so we'll be displaying it using CV2's IMShow only instead of matplotlib. Okay. So so we'll be needing only CV2, right? Now here we have defined a function, similar function, nothing else. It will take an image, it will create its copy, it will detect a face using detect multi-scale function, right? And it will take as a parameter this face. These are the two parameters that we are used to seeing by now, right? So these two parameters will be used to control the detection, right? So these are the general settings that works in most of the cases. So we'll go ahead with that only, right? And next, all of the faces that are detected will loop over all the coordinates and draw all the bounding boxes on that face and return the image with the bounding boxes, right? So this is the function that we have already seen, and we have used that function here also, right? This is the same function. Nothing has changed up till here, right? So here we have changed the color and the width of the thickness of the bounding box. Now the color we are using is green, right? So it's basically blue, green, and red channel, right? So blue and red are 0 and green is 2. So our bounding boxes will be green in color, right? Now the next step is let's load the cascade file, our file which will be used to detect this faces. So we'll use the same thing, same method, cv2.cascade classifier, and we'll pass in the XML file, path to the XML file. So for me particularly, it is inside the data folder. File's name is harcascade underscore frontalface.default.xml. We have seen this out. So this is our face cascade classifier. Up till here, everything is same, right? For image and for video also, right? Now, in case of an image, what would be the next step? We'll use this function detect face, and we'll pass an image to it, and it will return to us the image with the bounding boxes. Simple as that, right? But in case of videos, right? A video, we know that it is collection of frames. It's a collection of images. So for that, there is a different method in OpenCV that we use, and that is called cv2.video capture. Right? So what will this method do? It will basically read the video and it will give it to us frame by frame, image by image. One by one, we can read images through this video, right? So that's why this function is helpful over here. So basically, we can use cv2.video capture function, and inside that we'll pass the path to our video file, right? So I have already sent you this video also through WhatsApp. For me, it's inside the data folder, as you can see, face_walking.mp4, right? So we'll pass the path data inside the data folder. Name is face_walking.mp4. Right? Now, if you want to run this thing on your webcam, right? If you are working on a laptop or if you have external webcam, if you want to instead of a video, if you want to run it on a webcam, what we'll have to do is just pass 0 inside. When you pass 0, what CV2 does or this video capture method does is it looks for your primary camera. Whatever is the primary camera of your device, it will load that. It will read frames from that. Okay. So 0, basically the primary device for any laptop is its webcam, right? If you have a desktop and if you attach an external camera to that, then that would be your primary camera device, right? So it will read frames from that. So if you want to read from your webcam, just write 0, right? And if you want to read from a video file, just pass in the path to that file. In our case, we'll detect faces from a video, right? So we have passed the path of a video. This is our object, right? So we have a tab object for this video capture file, right? Now using this object, we can read frames one by one, right? So we'll just start an infinite loop, right? While true, right? So true is similar. When you have to write true, right? So it's always true. So this is basically an infinite loop. We won't come out of this loop unless we explicitly use the break statement, right? So we have given two conditions in which we will come out of this loop or this loop will terminate, right? So we'll look into that later, but let's start with how to read the frame. So we'll go inside the loop, and what we'll do is we'll read all the frames one by one, and we'll do the same thing, right? We'll read the frame, so that frame is basically an image. Then we'll have to do the same thing, right? Pass it to this function, it will return to us the image with the bounding box and display this image. Now again read the next frame, pass it to the function, get the updated bounding box frame and display it, right? So this is what we'll do. Right? So this loop is for that purpose, right? It will just execute one by one. It will just keep on running and it will keep on reading the frame and displaying the frame, right? So to read the frame, the function that we use is dot read method, right? So on this object will, whenever we call dot read method, it will give us the first frame of whatever the source we have given. If you have given a webcam, it will read a frame from the webcam. If you have given any video source, it will read a frame from the video, right? So in our case, as we have passed a video, it will read a frame from the video and it will return two things, right? One would be the frame itself, the image that is there in the first frame of the video, and the second would be an variable return. It would contain a boolean value, true or false, right? If the object didn't read any frame, if it didn't get any frame, the RET will be false. If it was able to read a frame from the object, the RET will be true. So basically we can check this RET to see whether the frames have ended or not, right? Suppose if the video is ended, right? So after the last frame, there won't be any frame, right? So in that case, RET will be false. So we'll check over here, if not RET break, right? So if RET, as soon as the RET gets false, right? If we didn't get any frame, it will break out of this while, right? So it will terminate the process, right? So it won't terminate the process unless there are frames, right? Until there are frames, it will just keep continuing. Okay. So what we'll do is we'll read the frame and then use our function, pass this frame or this image to our function, and we'll get in return the updated frame, right? The frame with the bounding boxes. Okay. So this part is similar to what we have done for an image, right? Pass an image and get the frame with the or an image with the bounding boxes. So we'll do that. Read a frame, pass that frame, get a frame with the bounding box. And after that, just display that frame, right? So now to display that frame, what we are doing is we are using cv2.imc. Right? So what cv2.imc does is cv2.imc just opens a different, an extra separate window, right? And on that window, it will display that frame, right? So it won't be here only, like in this case, our image was displayed in line here only, right? And the notebook itself. This doesn't happen with CV2. CV2 opens a separate window, and in that window you will get a frame, right? and this is basically the name of that window. If you want to give a title or name to that window, you can write it over. You can write anything. It doesn't matter. The second parameter is the frame that you want to display, that you want to show. So this is the image that we want to show. Its name is frame. So we have passed it, right? So this is the function, and here what we have done is we have used a method wait key. Basically, wait key, what happens? It waits for a particular this many milliseconds, and then it again continues, right? So what does it wait for? It waits for any key press, right? So for 10 milliseconds, it will wait for any key press, and then it will continue, right? And whatever the key is pressed, it will store its ASCII value inside this particular variable, right? And we have checked if c equals to 27. So basically 27 is for the escape, right? So after each frame, it will wait for 10 milliseconds to check if you have pressed escape key. So if you want to break out of the loop before the video terminates, what you can do is just press the escape key. As soon as you press the escape key, this condition will get true and it will break out of the loop. So this is another way we have added to get out of the loop. Okay, so there are two ways. Either if the video ends, it will break out of the loop automatically, or if the user presses an escape, it will break out of the loop. Now, this can also be used to control the frame rate. Right? If you increase it, suppose if you increase it to 1000, right? So 1000 milliseconds means basically 1 second, right? So it will wait for 1 second. So basically, it will display 1 frame per second, right? It will display this frame, read this frame, and display this frame, updated frame, and then it will wait for 1 second. Then it will again read and display this frame, then it will wait for 1 second. Right? So you can also use this thing to control the frame rate, right? If you want to slow down your video, you can increase this wait time. Okay, so it is two purposes. So basically, this is the thing, right? So we have run an infinite loop. It will read a frame from the video source, whatever the source is. It will detect or it will draw the bounding boxes on the whatever faces that it checks, and then it will display the frame, right? And it will continue this infinitely until the your source, either the video of the source is ended, right, or you press an escape, right? And after that, these two things are just resource capitalization, right? You have captured this video, so you'll have to release it, cap.release, and you have opened this one window over here, so you'll have to destroy that window also, close that window. So these are the two things to release those resources that we have captured. Cap.release and cv2.destroy all windows. Okay. So this is the basic code. Now let's just, without further ado, let's just let's just run it and look it in action, right? So for that purpose, let me just share my entire screen. Okay, so is my screen visible?
Yes, sir.
Okay, so from the command line, okay, so from the command line, we'll run this program. So to run it from the command line, simple Python, and then the type the name of the file, whatever is the name. In our case, it's face_detection_video, right? So it's this thing, right? So when we'll run this file, the entire code will be executed, whatever we saw, and it will work on our video. As you can see, a new window will open, yeah, and it will detect faces and draw the bounding boxes, as you can see over here, right? So our code is working as expected. It's reading all the frames one by one, drawing the bounding boxes on the faces that it has detected, and it's displaying it to us, right? So this is how we, as you can see, right? So the video ended, so it automatically got ended, right? So this is how basically we can use it, use our functions and all the things that we have learned, and we can deploy it on a video, right? It's nothing, just only one change is there. What is the change? we have to start a loop, right? First of all, capture the source, video source, and start an infinite loop and read frame one by one and do this part will remain the same, right? You have to do whatever we are doing on an image, right? We just have to read frame one by one and do the same thing on that frame, right? So this is how we implement it on it. So I hope you liked the lecture today and you got to know many things. I'll share the this notebook, face detection notebook that we have worked on. I'll share it on the WhatsApp with you guys, and this code also, the video code also I will share. So go through it, try to make changes to it, and see if you can come up with something new, or you can just get used to it, right? Okay. So that's all for today. I think I hope you would have. So if you have any questions, let me know.
Dear participants, any doubt, any question you may ask? Okay, no problem. If you want to ask any question, you may drop your question on WhatsApp group also. And very nice presentation and lecture, sir. Ayush sir, thank you. And
Thank you, sir.
thank you to all participants for joining today's lecture. So now we close the session, sir.
Yes, sir, sure.
Okay, sir. So yeah, tomorrow you will be continue, no? You continue your
Yes,
session.
yes. Tomorrow we'll continue with, we'll move on to the next topic. We'll start with neural networks. We'll introduce to the neural network deep learning world, and we'll start from that.
Okay. Thank you, sir, once again. And thank you, participants. We will meet at 3 p.m. sharp. Okay, thank you.
Yeah, thank you, everyone. It was good talking to you. See you tomorrow.